Okay, hi guys. So this is your topic 3 for heat and thermal insulation in building. Okay, so as usual, before you know what is the how it works for in building, how heat and thermal insulation works in a building, first off you need to learn about the characteristic of heat. So how it's being generated, how it's being measured, and how it's being transmitted. Once you know the characteristic of heat, then you need to know how the calculation it is to calculate the thermal insulation in the building. So heat is a form of energy. So in this topic, you will be covering four subtopic lah. First is the nature of heat. Second is the transmission of heat through the building fabric. And then third is the thermal insulation. And lastly, you have the condensation in building and humidity. So this humidity will be in terms of the psychrometric chart lah. So the reference is still the same. This is our two main core reading material. You have also additional reading material if you wish to. And at the end, you'll be able to describe the characteristic of heat in the building, in the built environment, and how to relate them to real life situation. You also learn a bit on the calculation and also the rule of thumb lah, on how to proper start it. Okay, so the first topic is the nature of heat. So a good representation of how heat changes is on this ice at 0 degrees to water and to steam. So a lot of what the skill that we have today is actually using the base of water. So if you guys notice lah, so this is a metric system. So previously we are using old system lah. So we can have the measurement of weight in, let's say in the old time we have in stone. Now is in kg. And then for temperature, we have different scale. The most popular one now is Celsius, but previously we have Kelvin, or we have Fahrenheit. So all of them have different value to it. And then for weight, as I mentioned, is in kg, gram. This is the new metric system. And previously it was in the old system is in stone lah. And then let's see, yeah, that's about it. And in measurement of distance, we are actually in olden days they use feet, and now we are using in meter or in mm. So it's a different scale of measurement. So it's to standardize so that everyone is saying the exact lah. So what I'm trying to say here is, why do we have this sort of standardization? So this is to ensure that the measurement is the same lah, from one country to another country, so that everyone is familiar with it and is more accurate. Okay, so for the first characteristic of heat, we know that heat is a form of energy which is also called thermal energy. So we learned about light and noise. So both of them are a byproduct of energy. So you use energy, it mostly is electrical energy, to generate light, and also we will be able to use it to generate noise. So their unit is in joules, represented by a J, and there's different methods to measure heat. So we can have calories, kilowatt hour, or the BTU, or the British Thermal Unit. So all these are different representation of heat. So being the most famous is calorie lah. So how much calorie a fire can burn off. So all these form of energy can be converted to heat energy. So an example is a mechanical energy of moving surface converts heat by friction. Either that or you have your electrical current which produce heat. So that's why you have different unit of measurement for your heat. Okay, so you have your power, which is a measure of the rate at which work is done or at which energy is converted from one form to another. So this power is actually represented by this P lah. So it's a measure of how much work can be done using this energy. So it's represented by this formula, which is heat over time. So it's how much energy this resource can be used to do a work, and is represented by this unit watt, and is in 1 joules per second. So J over S, which is represented by the heat divided by the time. So this is just a formula to which it shows how much work can be done by converting this resource to another form of energy. Okay, so more about heat or temperature. So one thing you have to realize is temperature is not the same as heat. So heat can be hot or cold, but it's actually decided by us. So the idea behind a heat being hot is by our judge of our brain. And temperature is a scale that is given to the level of hotness or intensity to a material. So 0 degrees can be just a normal temperature, but if you were to so 0 degrees can be a very cold temperature to us, but if you were to take it in terms of measurement of the scale of hotness, if you take it to a very extreme case or scenario in which you say it's out in the space, then 0 degrees is actually very hot. You can go to 4 to 5,000 degrees Celsius if you're very close to the sun, or if you're very far away from the sun, you can go to negative 3,000 degrees Celsius. So temperature is just a scale in which it can measure the degree of hotness in a body. So they are not the same as heat. So heat has this sort of properties in which they will try to make themselves equilibrium. So heat will always transfer from a high heat area to a low heat area. So we use a measuring material to measure heat because our body is very bad at measuring it lah. We can only through the contact of our skin judge that this is hot or this is cold. So the measurement of heat based on our sense is very inaccurate. You always use thermometer to measure how hot a surface is. So the most famous one is Celsius lah, in which we can always find that's always being mentioned. So we have a few old style of measurement, which is in Fahrenheit or in Kelvin. So the funny thing about this is they are using different form of measurement lah. And how this Celsius come about is by using water as a base of scale. So at 100 degrees Celsius, water boils. So this is a scale that is made based on the using the water as a properties. And at 0 degrees, water freeze. So Celsius is a scale of measurement based off on water. So in other cases or other scale of measurement, you'll find that in Fahrenheit, water boils at 242, but water freeze at 32 degrees Fahrenheit. And then at absolute zero, the is at negative 450. So the scale of this is a bit weird and funny lah. And then when you go to Kelvin, then you have water boils at 373 Kelvin, but water freeze at 273 Kelvin. So this sort of measurement is a bit confusing if you don't measure what the unit is. Because at 0 degrees, if you were to mention 100 K, then it might be at very cold. It will be at a very cold temperature. So this Celsius, this new measurement of temperature Celsius is done lah. So to give us a clear picture of the increase and decrease of the temperature, we'll be able to know how much is it lah, or we'll be able to compare it comparatively based on the number. So we won't, based on this Kelvin, if you were to say 273 Kelvin to 373 Kelvin, we know the temperature boils from here to here. But if you were to go below, then we won't know how cold you will easily get lah. But with the scale of the scale Celsius, we'll be easily be able to know how much increase in temperature based on this Celsius scale. So just remember lah, Fahrenheit is and Kelvin is the old method of measuring temperature. Then we have our specific heat capacity. So the specific heat capacity of a material is a quantity of heat energy required to raise the temperature of 1 kg of the material by either 1 Kelvin or 1 degree Celsius. So this specific heat capacity is how much energy is required by the material to raise its temperature by 1 degree. So higher heat capacity means is a very good medium of storing heat. So you want to have a high heat capacity for a medium such as like the boiler or the heating pipe lah, so that the material can hold more heat energy and be able to transfer this heat energy to another material lah. So a good specific heat capacity and a bad specific heat capacity, you can use its property to do different function. So if you want to heat up something, then you want to have a good specific heat capacity for the material. But if you don't want the heat to be transferred from one state from one medium to another medium, then you want to choose a material which has a low specific heat capacity. So you can see here, down here, you have a table. You can see that water is actually quite a good medium to hold and store heat. And then as you go lower, concrete is quite good also, ice, and finally you have our aluminium, which is not a very good heat holding material lah. So water requires a lot of energy to increase the temperature, and aluminium don't require a lot of energy to increase the temperature by 1 degree Celsius. So this is represented by this value lah. So experiment has been run, and they have found out that water needs 4,190 joules per kg to raise the temperature by 1 degree Celsius. So this is already around lah. So this can be changed and this value has been provided through experiment. Okay, so next we have our density of material. So different material have different density. Although a material may occupy the same space, but because of their density, a material may weigh more than another material. So for example, a brick and a cotton, let's say both of them occupy the same space. That based on that, we know that cotton is very light, but brick is dense and heavy. So even though they are occupying the same space, you know that cotton will always be lighter to pick up rather than brick. So why we want to know what is density is because uh, we have to learn that different material based on their different density that they have. They also have different heat capacity. So different material have different characteristic, and a density of a material is represented by this formula. So the mass, which is how heavy it is, usually in kg, is divided by volume. So the unit is in kg per meter cube. So if you can see the highlight here, so heat capacity of different material are compared on the basis of equal mass. But the equal mass of different material may occupy different volume of space depending upon their density. So how dense a material is will actually affect the heat capacity of the material. So this is what the statement is trying to say lah. Okay, next we have our sensible heat. So a sensible heat is the heat energy absorbed or released from a substance during a change of temperature. So this is termed sensible because it can be sensed by touch and measured by thermometer. So increase or decrease of temperature is a sensible heat. So when a temperature changes, when a substance changes temperature, the amount of sensible heat absorbed or released is given by this formula. So this H is the quantity of the sensible heat equals to mass of substance, which is in kg, and Celsius, which is the specific heat capacity, the C. And then you have your difference in temperature. So a sensible heat can be obtained through this formula. So remember, a sensible heat is changes in temperature. So you can sense and touch it. So example on how to utilize this formula for the sensible heat. You're given a storage heater which has a concrete block of dimension of 800 mm multiplied by 500 mm and 220 mm. So you are given the density of 2400 kg per meter cube and a specific heat capacity of 3300 joules per kg. So to make the calculation, to simplify the calculation, we are ignoring the heat losses. So calculate the quantity of heat required to raise the temperature of the block from 15 to 35. So it's asking you to calculate the quantity of heat required to raise the temperature. So this is a sensible heat lah. So a sensible heat is the temperature measured which you can sense. So you first you have to find out what is your mass, because it's not given to use your formula, which is the MC and the difference in temperature. You're given your sensible heat formula, which is H equals to mass and your specific heat capacity and also your difference in temperature. Two of them is given, but your mass is not given. You're given your volume and also your density, which is here, your density, and also your volume. So you need to use this density equals to mass over volume formula. So putting the known factors in, you'll be able to get your mass is 211.2 kg. So you substitute the value in here with all the known variable, and you get that the quantity of heat required to raise this material from 15 degrees Celsius to 35 degrees Celsius is 13.94 megajoules. So this M is a scale like the K. So it's a scientific scale. Let's see. Okay, so this is the scale the SI prefix. So kilo is always 1000 is in 1000, and a mega is in 6000. So if you see a G is in giga, which is 1 billion. So it's 1 million, 1000, 1 million, and 1 billion. So it's a SI prefix. So you guys have to be familiar with it lah. So this is fixed wherever you go. So if you don't have this M, then there will be a lot of zero behind here lah. So just for your info lah. Okay, so next is your latent heat. So a latent heat is the heat energy absorbed or released from a substance during a change of state. So this heat released or absorbed is with no temperature change, no change in temperature. So because there's no change in temperature, you will not be able to sense or touch or measure it lah. So it's given, the formula is given in terms of H equals to mass multiplied by the specific latent heat or change of state. So remember, latent heat is the heat generated to change the liquid or to change the state of the material from one state to another, either from solid to liquid or liquid to solid. So there's no change in temperature, but there's a change of state for the substance. So it can be represented by this figure. So you know that to convert your ice into water, you require a set specific of latent heat. But to heat up your water from 0 degrees to 100 degrees, you'll be looking at your sensible heat. So all material, when they are being heated up or cooled down, you're actually looking at the sensible heat. But when you're changing the state of the material from one state to another, from maybe liquid, solid to liquid, then you will have to look at the latent heat. So you're not increasing the temperature of the material, but you're changing the state. So this is the difference between latent heat and the sensible heat. Okay, so next we have this enthalpy. So this can be described as the total heat content of a sample with reference to 0 degrees. So the steam at 100 degrees Celsius has much higher total heat content than liquid at 100 degrees Celsius. So this is a measure of how much heat content is in a sample. And then we have expansion. So most substances expand on heating and contract on cooling. So because heat is a form of energy, when there's a lot of heat, the particles itself, they vibrate more. And then when it's cooled down, they will slow down. So in a railway, if heat is being done and the thing is not being built correctly, then you have a wavering line because the mass is reduced because the material expand. So the density reduced by a bit and the volume increased by a bit. Okay, so example 2. So this example will show you the way of how sensible heat and latent heat is being used. So you have to calculate the change of state of ice from 0 degrees to steam and how much energy is required to completely change this ice, 2 kg of ice at 0 degrees to steam at 100 degrees Celsius. So you're given the specific heat capacity of your water is 4190 and the latent heat is 335 for ice and 2260 for steam. So this latent heat is a change of state for ice to water and water at 100 degrees to steam at 100 degrees. And this specific heat capacity of the water, 4190 is a change of temperature for water from 0 degrees to 100 degrees. So with that, you know that for ice to change state for water, which is 335, so you just put it into the formula. You use the H equals to ml, which is a mass multiplied by the latent heat. So you get 670. So for the increase in temperature, you have to use this formula. H equals to mass, the heat capacity of the water, C, and then the difference in temperature. So you want to heat it from 100 to 0. So you just use 100 minus 0 and you get your value for your heat. And then you do that for your water 100 degrees to steam and you will get a set of value. So with that, you just add them together and you'll get your total heat required to completely convert this 2 kg of ice into steam, which is 6028 kilojoules. So here, if you can see, if you just multiply them together, you have a set of value which is quite large, which is 838,000 joules. So to simplify this value, to not write so many zero, you just put a k in it So this K is already universally understood is a SI prefix. So it's a scientific prefix. A K represents a value of 1000, multiplication of 1000. Okay, so we have this, which is a transmission of heat through building fabric. Okay, so let's finish this and we'll end it for this session. Okay, so now that we know that we know the characteristic of heat. Heat will always transfer itself to make the environment equilibrium. So it will always move from high temperature to low temperature. When you have a when it comes to building, we want to regulate the environment inside the building. So one of the way we want to regulate the temperature inside a building is we have air conditioning. So this will directly cool down our room. But in the olden days when there's no air conditioning, so what we have is fan and also natural ventilation, so our window. So to reduce the heat being generated inside a room, so we can just open the window in this room and heat can be directly taken off from this enclosed space out from this window into the environment. So that's provided if your room is very much hotter than the outside area. But if you're given in a situation where if you say it's overseas, where it's during the summer or it's during the winter where there's an extreme temperature difference, so heat will always go one way unless you have building services built in it lah. You have your heating system or you have your air conditioning system to counteract this change or this extreme environment outside. Okay, so because if you don't have this technology in your room to better cool down or increase the temperature in your room, the temperature, if you were to just use the natural method, natural ventilation, will always try to be equilibrium to the outside temperature. So if you are, for example, if you are overseas and it's during winter time where it's close to 0 degrees Celsius, so it's too cold for us. And if you were to open the window to allow the heat to escape, then it will our room will try to be equilibrium with the temperature outside, which is 0 degrees. So heat will be lost from inside the room to the outside. So to ensure a comfortable environment, we will want to have all these. Want to have the room that we are occupying be enclosed and the heating system on. So with the heating system on, we will be generating heat inside this room so that we'll be comfortable. So although our body itself generate heat, but if we were to be in a cold environment, it will never be enough lah. Because if the environment is like in winter in overseas, in Malaysia you don't encounter this sort of problem, but in overseas where they have 4 seasons, then when it goes to winter and they have snow, so the temperature outside is actually very cold at close to below 0 degrees. So if you were to just open the window and you allow the surrounding temperature to equilibrium all the temperature in your room, then it will be very cold inside your room lah, which is not desirable. So you need to have your heater system in place. But with only this heating system in place, it will never be enough because if your building is not well insulated, then your heat inside this room which is being generated by this heating system will escape. out into the environment. So you'll be losing your heat energy lah, which you are paying for it, which won't be ideal. So that's why you need to learn a bit of the transmission of heat through the building fabric. So when we are in a room and we want to be comfortable, we will also need to ensure that not too much not too much heat is being escaping out of our enclosed area into the environment. So you want to ensure that we have sufficient insulation to ensure all this heat is being trapped inside our room. So there's three ways of heat transfer. So you have to get this fact into your head that heat energy always tend to transfer from high temperature to low temperature region. So there's three methods of transfer. It's via conduction, convection, or radiation. So if you can see here, convection is through the heat energy transfer through the air. Conduction is through a solid material, and radiation through the IR lah, infrared lah. So convection and radiation is very similar. Okay, so here, a conduction is a transfer of heat energy through a material without the molecules of the material changing their basic position. So it's a transfer of heat in direct contact. So the better the conductor, the more rapid heat will transfer. So for convection, is the transfer of heat through movement of particles. So usually this medium of particles is our normal air lah. So air, although is a poor conductor of heat, but if you were to heat it enough, then you'll be able to heat the whole room with air lah. So usually for convection, air is always being used. Okay, so convection can occur in fluid also. So if you were to heat up a pot of water, you'll notice that there will be movement as the same with air. So they are through this bodily movement of particles, you'll be able to heat up the whole state of area, either it's in a liquid state or in a gas state. So here, stack effect describe the natural convection that occurs in building, causing warm air to flow from lower to upper stories. So this stack effect, you will always find it present lah, whenever you are. So whatever that is warm, usually air, it will always rise to the top of the ceiling or to the top of your building. So when you heat up something or you cool down something, this stack effect will always be present. So even in a fire lah, so warm air will always go up and cold air will always be at the bottom. And then finally we have our radiation. So radiation is a transfer of heat energy by electromagnetic wave in the infrared range of wavelength. So dull black surface have a high absorption and shiny surface have a low absorption. How the heat from the sun is transferred to earth is through radiation. So we do not need any medium of transfer. So previously we have our convection, which uses the bodily movement of particles. But in radiation, you are in infrared range of wavelength lah. So even in vacuum, how the heat from the sun reaches earth is through radiation. So it's not through convection lah. So three ways on how heat can be gain or loss is through convection, conduction, and radiation. Okay, so there are several factors in which how heat can be lost in a building. So the first is the insulation of the building lah. So if you have very good insulation, then you won't be losing so much heat from your building and your exposed area of building shell. So great external area or exposed area, higher rate of heat loss, the temperature difference inside and outside the building. So if you have bigger temperature difference, then there will be higher losses. And air change. So this air change is in terms of your ventilation of your building. So warmer air leaving a building, higher rate of heat loss. Exposure to external climate. So if your area has a high frequency of wind blowing, then you definitely have a higher rate of heat loss. And you have your efficiency of building of service in the building. So some wastage of heat energy used for water or space heating, and then reuse or recycle the heat energy used. And finally, you have the pattern of use for building. So different pattern of building usage, you have different rate of heat loss. So if you have more space exposed to a certain area, then you will have more heat loss lah. If you have a larger area of building. Okay, so heat is always being lost to the environment. But if the environment is very hot, you want to try to keep the heat from gaining into your room lah. But usually heat is always lost to the environment because we are always generating heat inside a building. So in a typical scenario, you'll always be losing about close to 35% to our wall, maybe 25% to the roof, 15% to our ventilation, another 10% to the window, and also 15% to floor. So if you add them together, it's close to 100% of how heat is lost through our building. So this is just a general guideline lah. It's not a true representative of all the building in all case of scenario. So this is just an approximate percentage for an uninsulated house heat loss. Okay, so there is two ways in which heat can be lost. One of them is through fabric heat loss. Another one is through ventilation heat loss. So the rate of the fabric heat loss, which is represented by here, is equals to the U value and the area multiplied with the temperature difference. So when you look at this triangle T, is always the difference in temperature, which is the same with this lah. So when you see this triangle, is the sum of difference between either it can be a temperature, but in other case, for other formula, this triangle is always the difference. So just keep that in mind lah when you encounter this triangle but there's not this you're not given this T, but with another value either Celsius or theta. Okay, so for ventilation is represented by this formula. So you have your C, which is the volumetric specific heat capacity of the air, and you have your N. So this N is your air change. So your V is your volume, and this is a formula for your fabric heat loss and your ventilation heat loss lah. So another example on how to use this. So example 3 is giving you a window measuring 2 meter and 1.25 meter. So you have a U value of 6.2 watts per meter square. You have to calculate the fabric heat loss through this window, given that the temperature difference is 20 degrees Celsius and 4 degrees Celsius. So it's asking you to find the fabric heat loss, which is using this formula, PT equals to U value, which is given 6.2, area, you got this is your area, and you have your difference in temperature. So 20 minus 4, you get 16. You just minus them together and you get that your fabric loss is 248 watts. So for P, this is a calculation of heat loss. You are given a building 4 meters long, 3 meters wide, and 2.5 meter high. So there's two windows, 1 times 1 meter with 0.6 meter, and a door of 1.7 meter and 0.8 meter. So you're given the following U value. For the window is 5.6, the door is 2.0, wall 2.5, roof, floor, and you're given the temperature difference of 18 degrees Celsius with 6 degrees Celsius. So you have to find what is the total rate of heat loss for this building. You're given also 1.5 air change, and then the heat capacity, which is 1300. So you have to utilize this ventilation heat loss formula. So you're given CV, you're given the number of air change, which is 1.5. You're given the volume, which you have to multiply from here. Your U value also, so you need to find the total rate of heat loss. So you have fabric heat loss and also your ventilation heat loss. So to make it easier, you can first draw out the dimension, the difference between temperature inside, the number of changes, and also your U value. Okay, so first off, you need to find your total fabric heat loss. So you're given the U value from the question for 5 components of your building here, and you're also given the area. So for that, to find out the rate of heat loss, you just use this formula. You multiply your U value with your area and your temperature difference. So you multiply these three variables, and you get your rate of heat loss for each component: window, door, walls, roof, and floor. So sum them up together, you get your total rate of fabric heat loss. Okay, because the question is asking for the total rate of heat loss, you also need to find out what is the ventilation loss due to air change. So next, you have to use the formula, which is this. The C multiplied by the number of air change multiplied by the volume and the changes of the temperature. So you get 195 watt. So with the previous total fabric loss 1734, you add them with your ventilation heat loss 195, you'll find that your total heat loss for this particular question or building is at 1929 watt. So this is how you utilize the formula. So it's just a very straightforward of using the value given and substitute it into the formula, and then you're adding it up together. Okay, so heat gain, there's different methods of heat gain. Usually is from the sun and also from any equipment or us being occupying the room. Okay, so the first is the solar heat gain. So there are several factors in which how solar heat gain can be affected. So if you are in a summer country and as opposed to a winter country, so generally a summer country with more sunlight will provide more heat gain. And then the next is how you build your building and the angle at which you build your building. So usually this will be done by architect. So architect will want to build a building maybe facing towards or away from the sun so that you don't gain so much heat energy. So this is the thing. This is how architect can affect how much heat can be gained on a building lah. So there's actually a study on how heat can be gained in a building, but this will usually be done by architect lah. And also the material of the building. So if you have more glass window or you have more transparent glass or window glass, you can actually reflect or absorb most of the solar heat from the sun. And also your material of your roof or wall. So depending on the choice of your material for your building, you can allow for more or less heat gain on how much heat gain can be given in a building. So the first one, two, three, four is depending on the on where you are at, lah. So the geographical latitude of the site, orientation of the building, so you are facing north or south, season of the year, local cloud condition. So how solar heat can be gained is determined by two factors in how you build the building. Either you're facing the building or away from the building, the material that you use for your building, and where you are at. So in a country with 4 seasons, then you will have a very wide range of temperature and how and the sun. And besides that, you also have your casual heat gain. So casual heat gain can be from people, your lighting, cooking and water heating, and also heat from your appliances. So you can gain a lot of heat from just occupying the said building. Okay, so because temperature will always try to make themselves equilibrium, so we want to ensure that the energy that we have, the temperature that is being regulated in a room is at a very comfortable level. So if you are comfortable at about 16 to 18 degrees Celsius, you want to ensure that the room is being regulated at around that temperature. So that if you have any appliances in the room, any heat gain from the, let's say, appliances you have in your room from your laptop is actually being reduced by another appliances, maybe your aircon, so that you will be able to maintain a very constant and comfortable temperature. So this process is actually represented by this formula. So you know that our heat being lost is through our fabric heat and ventilation heat, but we can actually gain heat from solar and casual, and also finally is our energy for heating or cooling. So this four is standard lah. And finally, we have our additional variable in which we can input to change our environment. So usually we can have a air conditioning or a heater in a cold country to regulate the temperature inside a room so that we feel comfortable. Okay, so we have our last example lah. So let's go through this quickly, and then we have a long break, and then we come back to continue this topic. So example 5 is the seasonal energy requirement. So over a heating season of 33 weeks, the average heat loss of this building is 2500 watt for fabric loss and 1300 watt for ventilation loss. So you're given the value for your fabric loss and ventilation loss, so you don't have to calculate it. So this window have areas of 6 meters square facing south, 5 meter facing east, 6 meters square facing north, and is occupied by 3 people, and cooking is by gas. So you have to find out what is the seasonal heat loss, seasonal heat gain, and seasonal heat requirement. So the rest of the value is given in table 1 and 2. So it's in this table, table 1, this table 1, and this table 2. So the total rate of heat loss, you can find it just by adding the fabric loss and ventilation loss. Add them together, you get 3800. So energy loss is equal to the rate of heat loss multiplied by the time. So you know that your time is 33 weeks. Given 33 weeks, you got 24 hours a day in a week, and then you have 60 hours, 60 minutes in 60 seconds. So you multiply these time factors together. So this is fixed for week, day, hour, minute, second. So 33 weeks, you have 7 days a week, 24 hours in a day, 60 minutes in an hour, and 60 seconds in 1 minute. So you multiply this together and you'll get this value. So this is your seasonal heat loss. And for gain, so referring to the table, you know that from your table 1, you know that for the window facing this, you have a seasonal total heat gain of this value. So using this value and having the area, which is for the south facing is 6 meters square, so you just multiply them together. So you will get that for your south is this value, east this value, and north another value. And from your casual gain, you know that there's 3 people, and referring to this table 2, body heat per person is 1000 megajoules. So you just multiply them together, 3 multiplied by 1000, and you know they are cooking using gas, water heating, and electrical. So you got all this value and you just add them together. So a sum of all this is your seasonal heat gain. So for your last question is for the last part for the seasonal heat requirement. So you just minus the heat loss and the heat gain. So you get the seasonal heat requirement is 53.712 gigajoules. So this is how you do it for your seasonal heat requirement. Okay, so let's stop